Hi everyone. So I'll be talking about some of the work that I've done throughout my PhD with Martin Escardo on constructive and predicative local theory in Univalent foundations. And I'll be talking specifically about the part on stone duality today. Let me start with an historical overview. So stone duality was first discovered in the context of Boolean algebras and stone spaces. And then it was generalized to distributive lattices and the so-called spectral spaces. The generalization is as follows. So the stone duality between Boolean algebras and stone spaces works by looking at the algebra of clopens of a stone space and the ultrafilters of a Boolean algebra. And in stone spaces, the algebra of clopens coincides with the algebra of compact opens. And upon this realization, we can focus on the algebra of compact opens and then go back and forth between the category of spectral spaces and the category of distributive lattices by taking the prime filters of a distributive lattice. We obtain a spectral space, and we have a spectral space. We look at the algebra of compact opens, and we get a distributive lattice. So this is the big picture. And we want to develop this stone duality in the context of univalent type theory, which is constructive and predicative by default. So the reason we're doing predicative mathematics is not philosophical or anything like that. It's very practical. We want to work in univalent foundations and in predicativity. So propositional resizing rules in univalent type theory, their computational behavior is not well understood. So that's why we're working predicatively. And to do things constructively, we work with point-free topology because stone duality in the context of point set topology is classical. It relies on the prime ideal theorem. But if we slightly change our notion of space, if we take locales as our notion of spaces, we can do it in a completely constructive way. And a locale is a notion of space that is characterized solely by its lattice of opens. So in point set topology, we have some set of points equipped with a topology, which is sublattice of its power set lattice. But in point-free topology, we don't insist that we work with a lattice of subsets of some set of points. We just work directly with lattices that may or may not consist of points. That's the idea. Okay, so let me pin down some foundational preliminaries. So I'll talk about the smallness of a type, and by that I mean given some type X in some universe U, we say that it's V small if it has an equivalent copy in V. And I will also talk about locally small types, which are types whose identity types are small. And by omega U, I denote the type of propositions in some universe U. And the propositional resizing axiom says that I can resize any proposition in the propositional resizing axiom between U and V says that every proposition in universe U can be resized to universe V. And omega resizing is a stronger form of it that says I can find a copy of entire omega U in universe V. And if you heard people say predicative mathematics is a branch of constructive mathematics and things like that, this is the reason. If we have the law of excluded middle, omega is just 2, so we can find a copy of it anywhere. So there is no classical in predicative mathematics. If we want to investigate things predicatively, we need to be doing constructive mathematics. And this fact will also be important for the work that I will present. So the propositionality of being small, the type expressing that a given type is small, if we have its propositionality for every pair of universes U and V, then the univalence axiom holds and vice versa. So this is univalence. It's a different way of formulating univalence. Okay, now we can start to do some point-free topology. So in the traditional development, a frame is a lattice it's a joint complete lattice with finite meets in which the finite meets distribute over the joints. And if we write down this notion of, so a frame is the lattice theoretic notion abstracting the behavior of the open sets in some topology, in point set topology. And when we write down this notion naively in type theory, we end up with something highly general with separate universes U, V, and W for the carrier set, the order, and for the families over which we take the joints. But we will be primarily interested in U plus UU frames, so large, locally small, and small complete frames. And in fact, it can be proven that these are the interesting ones, because it is well known that in predicative foundations of mathematics, complete and small lattices cannot be constructed, which was first shown by Giovanni Curie. But de Jong and Escardo gave a direct proof of this, where they directly show that if there exists a non-trivial small frame, then we get omega resizing from this. So, which means if we want to study point free topology in a predicative setting, we have to look at large and small complete frames. So this is sort of the broader context in which our investigation of stone duality fits. And by frame U, I denote so I fix some base universe U, and then by frame U, I denote the category of large, locally small, and small complete frames. And locales are the objects of the opposite of this category. And we pretend that locales are spaces. So we use the notation X and Y for them and talk about continuous map. And a continuous map F of locales is given by a frame homomorphism from the defining frame of locale Y to the defining locale of frame X. And we'll also need bases for locales, and a basis is a family of opens such that every open is decomposable into some opens falling in this family. And here we work with unspecified. So there is also a notion of strong base, which I will not need in this talk. But here we assert the unspecified existence of a basic covering family. And this is quite important. I'll get back to this. Okay. So we want to write down the definition of spectral locale, for which the first step is to pick up stone spaces and find the corresponding definition of spectral locale. And we find something that looks like this. Johnston uses slightly different terminology. He says finite element for compact elements. But this says a locale is spectral if every open is decomposable into a join of opens and a join of compact opens, and the compact opens form, they are closed under finite needs. And when we write this, first let me write down compactness. This is formulated using directed families in point free topology. We say that whenever we have a directed cover, then we can find some element in the cover that is above the open. This is just the covers of finite subcovers definition, but with Krotowski finiteness in constructed mathematics. And we define the type of compact opens. Sigma U is compact U, and observe that this is large. This lives in U plus. And we say that the locale is compact if its top open is compact. Now we define spectral locales. So the first three conditions here, SP1 to SP3, they correspond to the traditional definition. But we also additionally stipulate that this type of compact opens be small. So we say that the type of compact opens forms a weak base and it's small. And the category of spectral locales and spectral maps is given by, so we have a notion of spectral map, which is a map preserving, which is a map whose defining frame homomorphism preserves compact opens. And interestingly, the type expressing that a locale is spectral, because it has to assert the smallness of the algebra of compact opens, it uses univalence. Because of the fact I mentioned, because of the fact that the propositionality of being small seems to fundamentally use univalence. So this really seems to be an interesting interesting application of univalence that which we seem to need to show that being spectral is a proposition. Okay, so now we work with distributive lattices. Again, we work with some base universe U, and we define the small distributive lattices with respect to this universe. And by dlat sub U, I denote the category of distributive U lattices or small distributive lattices. And then we work with small ideals over the small distributive lattices. So a U ideal is a map into omega U in that universe that is inhabited, downward closed, and closed under binary joins. And we can show that this is a large, locally small, and small complete frame that is spectral. And this is the spectrum of the distributive lattice L, and we denote it by spec of L. So to contrast this with the classical situation, classically we obtain stone duality by working with ideals into two. Constructively, but impredicatively, we work into an omega with whose size doesn't matter. It can be living in, I mean, it has a copy in every universe. And constructively and predicatively, we map into the specific copy of omega that we have in our universe. And this still gives us a form of stone duality with respect to the category of large, locally small, and small complete spectral locales. So this is the contribution of our work. And to go from the category of spectral locales to distributive lattices, we use condition SP4, which gives us that the algebra of the type of compact opens has a small copy. And by transporting the entire structure of the algebra of compact opens, we obtain an isomorphic copy. So we resize the algebra of compact opens. So for every spectral locale X, we get a small distributive lattice X, meaning we can construct maps between the category of small distributive lattices and the category of large, locally small, and small complete spectral locales. And an interesting observation here is that even before we extend these to morphisms and define the functorial actions and so on, just by using univalence, just by turning the isomorphisms into equalities, we can obtain that we have a type equivalence between these two types, which means this extra large type of spectral locales is equivalent to this large type of distributive lattices. So we can resize this entire type consisting of large space-like objects into this category of finitary algebras. And this equivalence is already quite strong in the context of univalent foundations. Like these wildly different looking types are the same thing. Okay, so we extend this to, we define the functorial actions by, basically by transporting everything through the equivalences with the isomorphic copy of the algebra of compact opens, but I'll spare you the details in the interest of time. The key idea here is that we can work with omega U valued ideals of U small distributive lattices and get a predicative form of stone duality. And in my PhD thesis, I investigated point free topology in a predicative setting by looking at the category of such large locally small and small complete locales, and this fits nicely into this setting of predicative point free topology. Some other things that I would like to look at are, so for me, most interestingly, in previous work, Martin and I constructed the patch locale of a spectral locale. Also joint work with Igor Arieta. And if you look at this construction that transforms a spectral locale into a stone one from a lattice theoretic point of view, this should give you the free addition of complements into a distributive lattice. And yeah, this is something I would like to do. And Priestley duality, which is inherently related to spectral locales. This is also something that should work in a completely constructive and predicative way. And also in Tom de Jong's work on predicative domain theory, Martin and Tom studied algebraic domains in a similar setting. They looked at large, locally small, and small directed complete partial orders, and there are links to those, especially with what are known as superspectral locales. So the very similar duality should be possible if we study superspectral locales. And finally, everything I presented is completely formalized in AGDA, in type topology, in literate programming style, which means it is meant for it is meant primarily for humans to read than for machines to check. So please read it. Yeah, I think that's it.